My name's Madeline, and my 6-minute talk today is going to be about centrifugal pumps. So an overview of what we're going to be talking about. First, what is a centrifugal pump? Then how to find pump efficiency, how to read a pump curve, and then what the best efficiency point of a pump is, and what to do with that information. So first of all, what is a centrifugal pump? It's usually the most common type of pump in operation today, so you see a lot of them in the plants. It's a device designed to move a fluid by means of transferring rotational energy into the fluid, and this is done by a rapidly rotating impeller. This creates a low pressure in the middle, and that sucks the fluid in. This increases the fluid's velocity and pressure, and then directs it towards the pump outlet. And the impeller spins, is powered by a motor that's connected through a drive shaft. So here's a diagram of what this pump looks like. You see the suction port on the left side and the impeller in the middle, so the impeller's spinning really quickly. That creates that centripetal force that pushes the fluid to the outside of the casing. That creates a really low pressure in the middle, so all of the fluid is sucked in very rapidly. You see the drive shaft on the right, which is spinning the impeller. And then this is what it looks like on the right. This is what it looks like when you see it in the field. So this front part right here is the actual pump. And then you have your shaft and the shaft casing in here, and there's some bearings in there too. And then your motor's right here, which is spinning drive shaft. So this is how you calculate pump efficiency. It's the ratio of energy delivered by the pump over the energy supplied to the pump. So power out over power in. And we use this equation. The power out is the pressure change times the volume flow rate. And then the power in is just what horsepower is required by the pump to power it. And this ratio is never 100%, it's usually around 60 or 80% in the field. So a pump curve is something we can look at to figure out what efficiency we want to run our pump at. So it helps you select the right pump for your specific needs and application. And it's based on things that you need for your specific application, such as the head, which is water pressure, and flow, which is the volume flow rate, and we'll go into that a little bit more in the next slide. But it's really important for engineers to understand pump curves and learn how to read them. So you can either select a pump for a new project, or you can investigate a pump in an already existing project if something needs to be changed. So here's a little bit more on what you need to know before you look at your pump curve. So head and flow. Head is the height to which a pump can raise water straight up, as you can see in this diagram here. And it's calculated as a pressure differential that the pump has to overcome to raise the water. And this is important to know because this can be affected by the way your piping is, or some valves or fittings and stuff like that. And then flow is just the volume of water that a pump can move at a given pressure. So here's an example of a pump curve. We're just going to break it down and look at each piece because it's kind of complicated if you don't know what you're looking at. So number one, up in the top right is just your title box. That's just going to tell you name of your pump, what model it is, size and speed. And then on our horizontal axis on the bottom is our flow. So it's represented here in gallons per minute and meters cubed per hour. And then on the vertical axis is the head, which is in meters on the right and then feet on the left. And number 4 is those numbers over these numbers, because sometimes you want to trim your impeller if you want different results from it. So if you have a different diameter, it'll show you where you fall on that. These dotted lines right here show your horsepower, which is just how much power you'll need to run a pump at that specification. Number 6 is your NPSHR, which is net positive suction head required. So that's the minimum amount of pressure on the suction side of the pump, and if you go any lower than that, your pump's going to start cavitating, which means it's going to get such low pressure that whatever's in there is going to start boiling, and then you get bubbles in your pump, and you don't want that to happen because that will eat away at your impellers. So those are these lines here, and we just don't want to go any lower than that if we're running at that speed. And then these lines are our efficiency. So that's the ratio we were talking about earlier. Usually 60 to 80% is where people like to run their pumps. And then this line all the way over here is your minimum flow. And that's just from your spec sheet. That's just something you don't want to run your pump lower than. So the best efficiency point is a point on the pump curve where the pump is going to be operating at the highest efficiency for your needed parameters. Good pump efficiency just means that your pump is not wasting energy in order to maintain its performance point. But usually pumps are sized for performance rather than peak efficiency, because a lot of times people want to get more product out of it rather than maintain the pump. So usually increasing horsepower to increase this performance leads to the pump breaking faster than it would if it was operated at peak efficiency. And this is called operating off the BEP, which is very common when you're in the plant, because a lot of the time you want to process more product than they care more about making money than keeping all the pumps healthy for as long as they can. So here are some problems with running off the BEP. It adds energy cost because you have to fix your pump so much. It increases risk of failure. It can cause cavitation. Like I said, that's when those bubbles get in the pump. Excessive vibration of the pump, increased operating temperature, and repeated failures. And in conclusion, centrifugal pumps are widely used in the industry. They increase the energy of water through rotating propellers. And learning to read a pump curve is important when designing new systems and improving current ones. And while it's best for the pump to run near the BEP, it's usually run at a higher production rate to process more product. And this can cause issues for the pump, so it should be done with caution. Thank you.